Our next guest is one of the most exquisite experts when it comes to this field. He's a founding director of the German Research Center for Artificial Intelligence, and he developed DFKI into one of the world's largest research centers for AI, with more than 1,300 employees, more than 50 full professors, and 100 successful spin-off companies. He's a professor, and he's also a pioneer of AI in Germany as well as in Europe. So welcome on stage, Professor Wolfgang Wahlster. Here's your remote.
Thank you very much.
And the stage is all yours.
Thank you.
You're welcome.
Good morning. My topic is AI for a particular application area, namely Industry 4.0. First of all, what is Industry 4.0? It's the fourth industrial revolution. We already had another 3 revolutions. The first one was the introduction of the mechanical loom. Second one was mass production. Most of you know this from historic books. The division of labor was powered by electromotors. Electricity was the key for the second revolution. And the third one also was very successful. It was the introduction of IT, computers. The first robots were installed in factories. And now we are in the middle of the fourth industrial revolution, which we started here in Germany and Europe first in 2011. So about 10 years ago. So we have now 1 decade of this revolution, and we have another 10 years to go to really have all the factories which we have, legacy factories, transformed into factories of the fourth industrial revolution.
In the future, machines can perhaps even identify the potential for optimization automatically, coordinate among themselves, and involve humans if needed. But that's not all. Machinery and plants have to be even more flexible in the future. Production is moving away from mass-produced goods. Increasingly important are highly individualized products that can nevertheless be produced efficiently. To enable a rapid adaptation to changing requirements, consistently defined interfaces are needed. Principles like plug and play can also be implemented in production and considerably reduce the effort involved in the conversion of a plant. The smart product knows everything about its individual configuration, its customer, and its destination. The soap bottles with white stoppers have different destinations than the soap bottles with black stoppers.
There are some key economic drivers, of course, behind every revolution. And this one, the fourth of today, is batch size 1. So we have a very small lot size. We have the possibility of mass customization. Low volume, high mixture production is one of the important keywords here. On the other hand, of course, you all know, the product life cycle becomes much shorter. You have to exchange your iPhone every second year at least. We have a very high product variability. If you order a car, you have millions of possibilities to configure your new car. Therefore, we need multi-adaptive factories because there is so much insecurity in the market. We have volatile markets, we have demands up and down. We see this currently in the automotive industry. On the other hand, especially in Europe and in Germany, Japan is another example, China is beginning to have this problem. We have an aging society and we have a lack, actually, of skilled workforce. And finally, you all know about the Green Deal. We have to come up with solutions in manufacturing which are resource sensitive, which are really environmentally friendly, and in the best case, they have zero emission. In 2010, our then Chancellor, Angela Merkel, asked Professor Kagermann, who was the CEO of SAP, and myself, to come up with some future projects which are really revolutions in technology. And we created the idea of Industry 4.0. We had a lot of discussions with the Chancellor, and in the end, this was released. It was a big funding program. We have founded a platform and actually started in 2011. I gave the first talk at the Hanover Fair about this topic together with the Chancellor, and then we published our first papers. Up to now, 90,000 papers with the keyword Industry 4.0 have been published worldwide. Currently, in Europe, industry and academia are investing 140 billion euro per year on this topic, and we just started in Germany a new funding project for foundational work on Industry 4.0, because there are still a lot of open issues, of 5 billion euro only for basic research in Germany. So this Industry 4.0 concept is now a term which is known, you can check it out yourself, worldwide. If you go to China, Beijing, you talk to the ministry, they all know the keyword Industry 4.0, and they know it comes from Europe, in this case from Germany. It is recognized as a German word in a certain sense, like kindergarten or Autobahn, which are really also used in the United States and in English-speaking countries. So the idea of Industry 4.0 is very much based on data, data-driven production. You already saw in the video clip that we have the notion of a so-called digital twin. This is a virtual model of the physical object, and it's all the lifespan of an object. This digital memory is changed. It can become active. It can complain about the conditions in which it is injected. And you see here that AI, because AI for most parts is very much data-driven, there is a cycle from the smart factory, which produces a lot of data. We also have the smart product, which is produced at the smart factory, which also, of course, generates a lot of data. And this data is again used for smart services, which are key for smart products because they are added value for the customer. And then this data from the smart service is again feedback into the smart manufacturing and so on. You have this, feedback loops, and this keep the economy running. As I said, this brand is now very well known. I was shocked when I was invited by Elon Musk to his factory, the first Tesla factory in Fremont in California. They gave me the business card of their engineers, and you see they have on the business card Industry 4.0 liaison. Or in China, Lenovo, when I was invited there 2 years ago, I gave the keynote at the Lenovo headquarters for the CEO and CTO. Again, they say, father of Industry 4.0. It's in the 5-year plans of the Chinese government up to 2025. They want also to convert a lot of their factory to this standard. And in the US, there's even in Cincinnati, the so-called Industry 4.0 demonstration city. Yeah, very interesting. Anyway.
It features various production capabilities due to its modular design. We have included 4 new core elements in our system: a module exchange with automated release, adaptive AI methods based on deep neural networks, a Gaia-X connection, as well as modern scalable system architecture. We intentionally chose a simple product for the manufacturing process. A USB memory stick in the form of a studded brick can be individually configured. The customer can select from various colors available. The brick is mounted as desired at the assembly station. Then it makes its way to the data entry station, where process and customer-related data is stored on it. At the end of the line, the state of the final product is compared to the initial order using AI methods before the USB memory stick is output to the customer. An optional production photo is linked to the quality control data button. This option requires a special module to be available in the system. A notice is displayed on the operator's tablet, and the operator gets instructions that this module must be installed in the plant. The tablet now displays detailed worker assistance that provides step-by-step guidance on how to proceed safely through the plug and produce process. The special positioning elements on the stations and the plant system ensure that it is properly aligned, while electromagnets guarantee stability and occupational safety. Each work step must be manually confirmed before the process can continue. This helps to avoid safety issues. An intelligent new connector was developed especially to meet the requirements of modular and autonomous production systems. In this form, it serves as a model for standardization. Manual approvals lead the worker to a legally compliant plant operation. A certified and documented release is prepared at the end of each module exchange. The implemented security elements provide additional protection against unauthorized access. The newly installed module enables the quality control and the related picture, which is later flashed on the USB memory stick. The customer can also select options that require access to external suppliers. For example, we use the orange-colored studded bricks that can be ordered automatically via the European GAIA-X platform and delivered from the Netherlands. Via the GAIA-X node and connection, the production is triggered and the studded blocks are delivered and integrated into our system. On-site production is also possible, and the customer request can
This type of distributed production is very important. We also have some real labs now with Czech Republic. We have one with China, as I said, and also with the US. Key components of Industry 4.0 are the service-oriented cyber physical production systems. And this means, as I said, that the object which is to be produced has its own semantic memory, which we call a digital twin. And from the beginning, the specification of the customer's wish and demand is stored on the object itself. So it's you can imagine it's like a marketplace. The emerging product is looking for production machines which can turn it into its own, specification. So it's a complete inversion of the production logic of Industry 3.0 production, because there the machine was looking for an object with a certain identifier and then doing some job which was predefined. This is no longer the case. Here we use mobile robots, or sometimes we say that that's the taxi of the product. It brings the product to wherever there is a free station which will fulfill the job which is specified in the digital twin of the product. So it's completely other way. And when you think about it, you immediately understand that this is the way to go to mass customization, to have very small batch sizes, because it's the most flexible system. We already mentioned the term plug and produce. You bring in a new machine, and after a couple of seconds is already in the process. You don't have to reprogram anything, because this machine offers a certain service, and this service, if it is needed on the marketplace, the product will find it and go there and do the machining. So here you see the way from the emerging product, finding the way through the factory, and finally also by machine-to-machine communication, exchanging the current state of the produced product. And therefore, we invented also what we call the administration shell. This is already an international norm, which is now distributed via ISO, International Standardization Organization, so that we can make sure that the manufacturing machines of many different companies and nations can be coupled in a reasonable way. And this means that, for instance, in the product memory, we say what are the required capabilities of the next step in production, what kind of machines do we need, what is the process, and this is all stored, and then we compare the offered capabilities and the required capabilities. We match them on a semantic level, and then we have automatic also production planning. And as you see here, plug and produce means when you bring in a new machine, the machine is not just the physical part and the communication part in terms of IT connections. Yeah? Of course, this is all based on Ethernet, industrial Ethernet, but the more important step is that it comes with an ontological description of what this new device can do, what it offers on the market for the production in the factory. That's a key idea. And one can say with Industry 4.0, software plays a much more important role than ever before. Because today we still have the machine in the foreground, manufacturing machine, with some software. But in the future with Industry 4.0, and we see this in the first factories which are completely compliant with Industry 4.0 standard, the software is the key and the machine is much less in focus. Now, of course, we need AI to make this happen. And AI means that we have semi or fully autonomous systems. And this completes the whole circle of cognition, namely, first of all, sensing. Then when you sense something, you have to understand it and think about it, what it means for your current goals. And then, of course, you have to act. You see this here in the Rubik Cubes example, yeah, that the act is done also by a robot. Our strategy for Europe and especially for Germany, Switzerland has a similar economy, also parts of Italy, France, is that we have some export products which are very successful in the market. In Germany, of course, these are the cars. But it's also manufacturing equipment which exported. When you go to a factory in the United States, for instance, the Tesla factory, it's 90% of the machines which are installed there come from Germany or Switzerland. And the same is true in China. Most people say this is all Chinese. This is not true. In the very high precision manufacturing, of course, these machines, the equipment from Germany is extremely important. Medical equipment is also very high volume. Then, of course, home appliances. It sounds a bit trivial, but as you know, Miele or Bosch, these are worldwide the best home appliances. Even Steve Jobs, he tested, I think, more than 14 washing machines, he once told me privately, and he decided to go for a German model, not a US model. Same is in agricultural machinery, and of course, Airbus is also a success story. So these are 6 top export articles, and what we want to do is with Industry 4.0, by the injection, vaccination, so to speak, with AI, we want to go to the next level of these products so that we are leading in innovation for these products, product groups. AI itself is not so new. Many people say it's AI hype now, but actually AI, as most of you will know, was already founded. The term was coined in 1956 already by McCarthy. And the first things which were done, actually, and most people don't know this, were neural networks. When you go to the first conference proceedings, it was full about machine learning. So machine learning is not really new, but at that time, it was very primitive. What you could do is just to recognize the digits from 1 to 9 when you dictate them with a neural network. Then we have a long time with knowledge-based systems because it was the idea that if you give knowledge to the machine, you empower the software to do real intelligent things, but it turned out this was much work to handcraft all the knowledge. So then we had the wave of machine learning, data-driven machine learning. But now in the last years, it turned out that only machine learning is also not good, because you cannot derive everything from data. You reinvent the wheel, and sometimes it wouldn't work. Because yesterday in the talks, you saw a lot of extremely important physical laws. I mean, Maxwell's equation, Schrödinger equation, Einstein's theory, and so on. When you want to rederive this from data, it's mostly impossible. You will not find, because these were genial ideas and took a long time also in physics to find them. And also it's nonsense. We know these equations. Why not give them to the computer, and why should we derive them from scratch? This doesn't make sense. So now we have the era of combining knowledge-based, so symbolic methods, with, of course, with data-driven methods, because machine learning is extremely important, especially for perception. Here, this picture should tell you that, of course, Industry 4.0 is based on data, but the first step in the digitalization wave was that we first of all record all data in a digital way, we save it, we transmit it, and we process it by digital computers. This wave is already over. I think every company has this. Yeah? If not, they will go, bankruptcy in the next years, I would say. The second wave is much higher. It comes like a tsunami. This wave means that the data is not only machine readable, but it's also machine understandable. And this is a big deal, because then the system itself can decide, when I understand this data, what should I do given this data? What action should I take? How can I make money with this insights I get here? And the active usage, not by humans, but by the software itself, that's the real deal, big deal now, what we call machine understandable digital data. And this is the era of artificial intelligence. As I said, the first decade of Industry 4.0 is just finished this year. Next year we start the second decade, and here the machine learning is even more important. We have machine understanding, and we have a practical use of the insight of this industrial data. DFKI already works with this issue. We had the first smart factories. We built some smart factories for Bosch, also together with Volkswagen, for instance. BMW has accepted this concept. Siemens is very much involved. So big companies, but we also exported, as I said, because we have very good shareholders like Google is very interested, Microsoft in the US, SAP, of course, Intel, NVIDIA, and so on. So it's a large ecosystem already. And I want to emphasize that the machine learning is also very important to build the system. Because in the past, when you go back 20 years in computer science, everything was based on the programmer who had, a given algorithm encoding, and he or she encoding this. And so actually the knowledge about the domain was just in the head of the programmer. The problem with this is there are very high development costs, as all of you know. It's restricted adaptability of the code when you have new requirements, and also the system was not able to explain what it is doing. If you call a tax advising system and say, hey, why do you recommend this? It cannot do, because if it's only encoded, in Java or whatever, the system is not able to read its own code and explain. This was much better in the knowledge base domain, when you just give the system facts, rules, models, and the system really has engines which evaluate these rules. Of course, the system can also give an explanation how it came to a certain conclusion. But the big disadvantage, again, is that you have a huge effort to, first of all, create the system, and then to keep it on a current base. You have to maintain the knowledge base, and this is very costly. With the machine learning, if you have the good training data, what you can do is that the machine itself, the machine learning system, without any coding by a human, learns how a certain task has to be done. The bad thing about this is that the explanation capabilities, and I will come to this later in the more technical part, that is still in its infancy. It's not impossible, but the explanations you are getting are not completely convincing, especially for lay persons. Yeah? For the experts in neural networks, I can tell you I know how the networks is working, so I can explain a little bit, but for the normal user, it's not good enough. Here you see a deep learning network in action. So this is really in real time. So you show, when you look through your eyeglasses, and this is augmented reality, but the interesting thing is not the augmented reality, but that the automatic recognition of all these objects, you see gift box, scissors, with very different views. So there's a small camera in the glasses, but the AI part is the perception and the recognition of the object. 10 years ago, something like this would not be possible. It was very slow. I worked on image sequence understanding already 20 years ago, and I can tell you we had a hard time even to recognize moving cars in Hamburg, where I worked at that time, because everything was extremely slow and not very high probability that you recognize the right object. And here you see it works really perfectly. And this is one of the components of Industry 4.0, the automatic recognition of all objects in the environment. And this is a big deal. Now, how is this done? We have very good tools available, some of them even in open source or as free software. And the only bottleneck with the training of machine learning systems today is that it uses huge computing capabilities. Therefore, of course, yesterday we had some talks about quantum computing, and this is a big hope that some of the things can be even increased in speed. But also the energy which is consumed by these learning algorithms is quite significant. So there's also a lot of to do. Also, there are big successes. And we have machines, for instance, in DFKI, we have now the largest cluster of so-called graphical processing units, computers based on machines from NVIDIA. We have 60 petaflops computing and so on. But believe it, our electricity bill is extremely high right now. To train simple networks costs a lot of energy. And you see such a learning process here. This is very simple. It's the so-called TensorFlow, and you see that these lines between the nodes are the neurons, then typically you have a multi-layered network. Here on this slide, there are only a small set of layers. Today we have networks we train with more than 2,000, 10,000 layers and each layer is a level of abstraction of features, and we have billions of neurons in such networks, and then we can really perform sometimes even with a superhuman performance. And you know all the success stories of deep learning, for instance, in the game of Go. Chess there is no game. The last game which we cracked in AI was actually poker. Poker is even harder than the Go game or check. Yeah, most people don't know this, but poker is extremely hard to. And again, the world champion in poker was the system. Won this game against the world champion. Now, also what we should remind us is that when we have learned a certain algorithm, a new network, then this trained neural network is not used in this way as it was learned from scratch. But we use different and a lot of different techniques to optimize and to compile this neural network so that it becomes more compact. Because especially in Industry 4.0, of course, we want to run these networks on smaller machines, in many cases even embedded electronics in a device. And this wouldn't work when we just use the learning result. So we have special runtime environments for the optimized network, and this works very nicely. There are many examples where we implement such a network on a small chip. One of the big challenges in Industry 4.0 is that we, of course, will not have factories without humans. This is complete nonsense. We need humans, human experts in these factories. Still, for the next decade, they are urgently needed. But we also want to achieve a zero-defect manufacturing. That means with AI, we have the possibility to watch the workers in action, and as soon as they make a little mistake, we will guide them to repair it or to correct the error, so that at the end of the line of production, we actually have zero defect. And this is quite new. If you have a car, like, for instance in BMW, it takes more than 20 minutes at the end of the production line to check the car. And in many cases, the car has to go back in the cycle because some problem was recognized in the end checking. With this new Industry 4.0 production lines, where you have incremental quality checking by sensors, by AI, there is actually no final checking, and everything is okay. You save a lot of money and time, and the quality of the products is higher. Here you see a simple example that even the tightening of a screw, very simple task, is watched by the AI system, and there is an alarm if something is done incorrectly. And we do this by various sensors, not only simple optical sensors. Sometimes we have to use sensor fusion with different technologies. Often we use, of course, laser scanners. And what is interesting here is also that we can give the system models of a proper manufacturing process. And these models are also understood by the AI system, and it is compared with a digital twin, what's going on. So the system has picking analysis, mounting analysis, hand postures, of course, and the whole body analysis of the worker, and it compares every step on the event bus with the original, good plan for the manufacturing of this part. And we even integrate a lot of sensors into the workers' wear. So also as a health issue, because as I said, we have an aging population. We need workers which are going on in factories up to, let's say, 68, 70 years and are in good health. And this means that during their early stages of the career, we already monitor their behavior and warn them if they have problems. For instance, of course, the chest is watched, the heart rate, the posture of the lower body, of course, the shoes, the pressure on the shoes, the posture of the head, the back, and the arms, and so on. And this is very important. Now, as I said, we have a lot of methods which are based on a numerical neural networks, but if it's possible, we also work with theorem-proving methods and more formal methods, which come from automation of mathematics. And here I give you an example of another very successful method. This is so-called constraint satisfaction. We have thousands of equations which would not be solvable by a human by hand, but the system does this automatically. We work here together with IBM and the Google group on the constraint satisfaction, and we came up with a method which actually can fully automatically design the cable harness of cars. In an electrical cars, the more mass customization we have, it's very complex. We have 2,000 cables. For every cable, we have a set of equations. So we have thousands of equations which you have to solve with constraints, and this is actually possible with the methods we have developed in AI. And the good thing here is fully deterministic. Yeah, there is no neural network involved here, but you, at the end, you can say this cable harness is absolutely correct, and then you drive the robot, you saw it working, doing this cabling. And the cable harness production currently, 80% of the cable harnesses are done by hand. Yeah? And what we do with such a system is we can do this fully automatically in the smart factory. As I already said, in AI, we always have a pendulum of symbolic methods and numeric methods. And you cannot say one is better than the other. It depends on the purpose. And in most cases, for a real application, you need both. That's what we call hybrid models. Symbolic methods are very much based on logic and algebra in more like theoretical physics in AI. On the other hand, numeric methods are also very important. Like in experimental physics, you have stochastics, you have analysis, and so on. And of course, semantic networks, this is a key word in the symbolic domain. The same for constraint solvers or unification systems, so-called inductive logic programming. All these theories are very much very successful in symbolic AI, but alone they also in many cases don't do the job. Especially in robotics, again, you need both. For higher level cognition in robotics, symbolic. On the low level, sensory level and motoric level, the numeric methods are very successful, and including the deep learning. So the new formula in AI is actually you combine deep learning with other methods. For instance, knowledge graphs, terminological logic, which are well known. Now, I already said that in many cases, the human worker has to work with a machine together in a symbiosis. For a long time, we had robots which were like a lion in the zoo in a cave. Don't touch it, extremely dangerous. Please don't come close to these robots. This is the old industrial robots. The new robots, the so-called soft robots or cobots, they work together hand in hand with workers. And not only one robot with one guy, but we have have installed, for instance, in Volkswagen systems where there is a team of robots. So 3 different robots of different size with different skills with 2 humans working together in a team. So this is the future in Industry 4.0. And here you see a simple application at Audi where the robot grips something, gives this to the worker, and the worker installs it. And we have many such examples. Here you see something, actually, this is in Bremen. This, as you may know, in Bremen is a big Airbus factory, and they assemble the wings. Actually, all the hydraulics and the electronics is assembled and injected in and constructed for the wing. And here you see 3 robots helping a worker to install the so-called raceways. These raceways, in this raceway, you have all the electronics in a wing installed. And the worker even gets the right screwdriver at the right moment from our mobile robots. He will pick the next tool, going in the, to look for a new tool. And also the robots help the worker to fix something which has to be installed. Now your question will be, why doesn't the robot do this? This is not allowed for safety and security reasons, because it's so critical. If you use the wrong screw and you use the wrong screwdriver or the wrong momentum, the torque on the screwdriver, maybe later the airplane will crash. And therefore, the worker itself has to, actually guarantee that he did the right job. And again, we observe what the worker is doing and can warn, but it's not allowed to do this completely with a robot. One big issue currently is that we want to integrate intra-logistics and the production planning. This is not done worldwide, and the first trial we have now is in the new Volkswagen factory in Zwickau. This is a factory which is completely dedicated to producing a really large volume of fully electrical cars. This is in Eastern Germany, completely new factory with 800 mobile robots running around, actually using this paradigm of Industry 4.0. If we compare, where are we? Comparing Germany with US and China, we can say that AI is used in the US mainly for advertising, for marketing, for introducing new B2C business models, smart mobile services, and financial service. Whereas in Germany, we do just the inverse. We go to B2B modeling. We have logistics, as I just said, Industry 4.0 applications. Of course, we are very strong in multilinguality because we are in Europe with more than 30 different languages, and collaborative robots is really a specialty. There were 2 companies in the US, but they went to bankruptcy. One was even bought by a German company, so we are leading in this field. On the other hand, China also is very good in retail and payment with AI. They do advanced manufacturing, and they are catching up, I must say, and they use a lot AI for education. Now, when we have a steady state of the art of Industry 4.0, we are not finished, because we have also to verify, to certify what we have done, because there are a lot of security and safety issues. Therefore, I was commissioned 2 years ago. I started to come up with what we call the German Standardization Roadmap for AI. 256 pages describing what kind of standards we already have here in Europe, which we have in the US, in China, and what kind of standards we still need to find. And of course, we need for all this machinery, including, in the end, also the products like autonomous cars, we have to have certification procedures like they are done today by TÜV for our cars. Let me summarize. A lot of AI technologies can be used, and you see here the Lego bricks. These are different methods I have mentioned in AI, and they are used for all the characteristics of Industry 4.0, and then I get autonomous systems, proactive systems, explainable systems, self-learning systems, and self-healing. Let me conclude with a short comparison of the human intelligence and AI. I'm often asked, what is the strength of the human? What is the strength in robots? And what I must say, the sensomotoric intelligence is much higher in the humans. Cognitive intelligence, and this is a shocking news maybe for most of you, already AI is in many cases much stronger than human. What is missing in AI completely is social intelligence and emotional intelligence. And of course, there are a lot of problems in deep learning, and I already mentioned some of them, but there's even more problem. For instance, machine learning systems cannot extinct what they have learned. Humans can say, oh, forget about it, I learned something wrong. This is currently not possible. You have to delete the complete system, and this happened to Microsoft already twice, to delete the complete system because some garbage was learned. Let me conclude. The export success is based in Europe on physical products, and they are based on software components which do guarantee top quality and zero error products. For interoperability of industrial AI components, international technical standards are urgently needed. Digital twins on every level of Industry 4.0 are the enabler of a circular economy based on industrial AI. Deep learning is not enough for the next generation. We need hybrid systems. And of course, AI technologies, as I have shown, are the key success factor for Industry 4.0. Hybrid teams of cobots and softbots and people are a challenge for research and multi-agent coordination. And finally, I think Industry 4.0 is very exciting because it brings together many AI fields in one of the most important fields for industrialized countries like Germany. Thank you very much for your attention.